So that brings us to letter D, and I know what you're already thinking. Mr. Wade, this is a college class. Challenge us, right? I was thinking the same thing because I thought the first few examples were just kind of too easy, right? Okay, you want a challenge? Great. Let's throw in a cosine. Oh, this is going to be fun. Now, again, I'm not trying to intimidate you or scare you. You always take math that looks hard and try to make it easy. Always, right? So you look at this, you're like, ooh, that is a little bit harder. Well, it is, but I want to circle this part right here, okay? Let's just pull this aside, and let's just talk about cosine of n pi. Okay, now what would you plug in first? You would plug in 1 for n, and you would get the cosine of 1 pi. Reason number 5,683 that you must know your sine and cosine graphs, right? They come up all the time. The cosine of pi is a valley, so it's -1. Now, next integer, plug in the number 2, and you would get the cosine of 2 pi. 2 pi is a peak because it's an even pi, which is +1. Then plug in the next integer, 3. Cosine of 3 pi is an odd pi, which is a valley. All odd pi's are valleys. All valleys are worth -1. Cosine of 4 pi is +1. So all that term right there is doing, it looks scary. All it's doing is it's making your first term negative, your second term positive, your next term negative, your next term positive. All it's doing is alternating the signs back and forth, okay? So let's focus on the rest of this puzzle. Let's focus on n over 2n minus 1, okay? Let's write it out just for fun. On a test, you probably wouldn't write out very many of these, but just to kind of show you, introductory level, right? Let's just see what's happening. Take 1, plug it into the two n's here, and you get 1 over 1, right? But the cosine makes it negative. So it's -1, isn't it? Now, don't we do an addition because sigma means keep adding? Okay. The second term, plug in 2 here and there. If you plug in 2 to these two, you get 2/3, but it's positive because the cosine makes it positive now. So -1 plus 2/3. Now the third, when you plug in 3 for n, the cosine is going to make it a negative. So even though sigma says plus, it's going to be plus a negative, which actually makes a subtraction. Here, I'll put it down here, but you should be putting it down there. Okay, out of board space already. Minus, when you plug in the number 3, you get 3 over, 6 minus 1 is 5. You get a -3/5. Interesting. And then when you plug in the fourth term, you get a positive on the cosine. So you get a plus. And then when we plug in 4, we get 4 over what? 7? All right. And then ... You see how these things always come in patterns? You see the denominator is going 3, 5, 7, 9, 11, etc. Okay, these things always come in patterns. Always. Look at the numerator. 2, 3, 4, 5, 6, 7, 8, 9, 10, because it's just n. All right. So you'll see patterns. But here's the big question. If you had a negative, and then you added some to it, and then you subtracted some from that, and you added some to that, now it's going kind of back and forth. This is the first time we've ever had this. This is called an alternating series, when the sine is alternating, and the cosine caused the alternating to happen. All right, so you can write this down. Alternating. It's an alternating series. That's actually going to be our focus for the next lesson, so we'll really get into these later, okay? I'll kind of give you a little hint today, I guess. But alternating series, alternating sine, okay? So here's the thing. Remember that old divergence test we were just talking about where the limit of n approaches infinity works? Well, okay. So you can't, this is something we've never talked about before in those old limit chapters. You can't do the limit of a sine or a cosine or a tangent because it keeps flip-flopping back and forth. So there really is no infinite limit. You can never pin it down. It just keeps changing to -1, +1, -1, +1. So what we do is we'll apply the infinite limit. This is what Mr. Wade calls removing the oscillator, okay? The alternating, another word for alternating is oscillating. Oscillating means back and forth, back and forth. Remove the oscillator and just focus on the n over 2n minus 1 because that's really what matters. All right? And I'm kind of getting you ahead to another lesson, but that's okay. Still, we're going to apply the infinite limit. Now, number 1, can you graph that? Not easily. So, 3 gems. Plug in infinity. You get infinity over infinity. Okay, dead end. Gem number 2. You can do the weaker, stronger game, or our newfound trick from the last chapter, L'Hopital's rule. If you do L'Hopital's rule, you'll end up getting the derivative, you'll get 1 over 2. If you do the weaker, stronger game and it's tied into the first, you also take the leading coefficients, which is 1 over 2. Either way you do it, you get 1 over 2. Okay, so removing the oscillator that is simply changing the signs, the limit of the rest of it, which you are allowed to do, is 1/2. Now, what was our marker here? What's our comparison? 0, right? If the limit is not 0, even though those fractions are getting smaller and smaller and smaller, it is not convergent. That means divergent, right? If it's 0, it's inconclusive. But it is not 0, so you know that this is a divergent series. How about that? Even when the fractions get small. Okay, so that's a good one to see with the oscillator in there. And by the way, if you wanted to throw the cosine back into your limit that we didn't do, we got 1/2, right? If you wanted to take the limit as n approaches infinity of cosine, remember you can't pin it down, it just keeps doing this. So that limit would have been does not exist. So if you want to, you could have proceeded and said 1/2, which was the fraction part, times the oscillating part, which was does not exist. 1/2 times does not exist is does not exist. And guess what? That's not equal to 0. So by the divergence test, it was divergent. Now let me give you a second superpower today, all right? I'll try to give you 2 per day usually, depending on the day, but number 2 of 6. This is called the alternating series test, and it's kind of what we were just hinting at a moment ago, all right? It has to do with alternating signs. So we know the discoverer of this one. Number 19 ranked, Gottfried Leibniz. And it took until 1714. He developed calculus in the late 1600s, separate from Newton, right? Completely separate, and sued. But in 1714, he discovered this alternating series test I'm about to give you. Kind of what we just did. And he sent a letter to his best buddy, number 81 ranked Johann Bernoulli. That was the first person he told. And he said, look at this. And Bernoulli verified it and said, yep, you got something special here. So, and it's kind of weird too. It's kind of crazy. If you have a series, an infinite series, and you rewrite it as b sub n, we'll call b sub n the side portion like n over 2n minus 1, and then we'll let the other part be the oscillator that's just making the sign go back and forth. If you remove the oscillator like we just did, and you only focus on b sub n, you can do just that limit, okay? But look what I wrote here for something we did not just discuss. If you do the limit as n approaches infinity of the non-oscillating part, and it turns out to be 0, that was inconclusive in the divergence test we first learned today. But if the sign alternates back and forth, the series equal to 0, the limit equal to 0, will converge. Wait a minute. Hold on a second. Okay? You don't have to add this to your notes, but if you want to, you can. All right? Or you can also put 1714 if you want to over there. Wait a minute. You remember the 1 over n we discussed earlier? You remember this one? Remember that was 1 plus 1/2 plus 1/3 plus 1/4, and we said it was going to get smaller and smaller, but it still doesn't converge. It actually diverges, which we won't prove until next time. Remember we said that? But if you put an oscillator in there, let's say it was 1 minus 1/2 plus 1/3 minus 1/4, and every other sign was negative. Or you could have started with the first sign negative and the third sign negative. You could have flip-flopped it. You're telling me if every other sign is negative, the subtraction is just enough to lower it and make it actually converge to a finite area or sum? Yes, that is exactly what I'm telling you. And that's what mathematicians and scientists did not believe until Leibniz proved it, and they were like, wow, I can't believe this actually worked. Okay? So, even if you have a typical series that is divergent, but you throw in an oscillator, sometimes you can get those to converge, which is just crazy. It's unbelievable. If you kind of see that, the beauty of that, great. If you don't fully understand it, that's okay. Your brain will click. So the whole point is remove the oscillator if it's an alternating series. Redo the limit. But this time, 0 is conclusive. In the divergence test, if there's no oscillator, it is inconclusive. So that is a huge breakthrough. I put a couple of disclaimers over here. They're not a big deal. B sub n is the non-oscillating part. So picture the fractions in the last answer we just got, but take out all the negative signs. Picture them as positives. Were they all greater than or equal to 0? Were the fractions greater than or equal to 0? If you remove the negative signs, the oscillator, yes. And they're always going to set that up for you. The alternating series test, though, only works if you have positive fractions once you remove that negative sign, or everything would be backwards. So not a big deal. It's always going to be that way. Okay. Also, b sub n needs to be non-increasing. So the fractions were not getting bigger. Okay. 2/3 is worth like 0.66666, right? Repeating. 3 out of 5 is only 0.6, smaller. 4/7 is only worth a smaller number. So yes, it was non-increasing, and non-increasing means either decreasing or stable. 2/3 plus 2/3 plus 2/3 plus 2/3. Okay, that would also be non-increasing. All right, so yes, this will always be set up for you on the AP test. I'll always set it up that way, so it's always going to work. You don't have to worry about that. But that is true, and in college they'll actually make you verify that it's non-increasing, and they'll make you verify that it's greater than or equal to 0. Okay, all right, moving on. So now we look at something that I call other oscillators. These are actually far more common than cosine of n pi that we just used. These are very, very, very common in high school and college for series, okay? -1 to the n, that is an oscillator. Try it. Take 1, plug it in. -1 to the first is -1. Take 2, plug it in. -1 squared becomes +1. -1 cubed is -1. -1 to the fourth is +1. All -1 to the n does in a series is just alternate the sign back and forth. Okay? Now try n plus 8 for the power. Take 1, plug it in. That becomes -1 to the ninth, which is -1 to the odd, which is -1. 2 plus 8 is 10. -1 to the 10th is -1 to the even, which is 1. -1, +1. You get the same thing. So if you have n, which you rarely see n plus 8, but if you have n plus or minus an even number, and you have -1 to that power, you're going to get this sequence, sequence for now, not a series yet. But if you have n plus or minus an odd number, that actually switches it, because sometimes you're going to need to make your own series and you're going to need to switch the signs. But I wanted the first sign to be positive. Okay, use this right here. 1 minus 1 is 0. -1 to the 0 is +1. Plug in 2. 2 minus 1 is 1. -1 to the first is -1. +1, -1. So it's oscillating, it's alternating, but the other way. So just kind of know those three types right there. And now we go to the very thing we were just talking about. What happens if you put an oscillator with 1 over n, that we earlier said 1 over n was divergent, but then you put the oscillator on it? Watch what happens here. So this is called, not the harmonic series, this is called the alternating harmonic series. Naturally, right? Of course it is. Alternating harmonic series. Yes, this is related to music also. Yes, my father indeed studied this with its connection between math and music. Really fascinating stuff he found out. So alternating harmonic series. You plug in 1, 2, 3, 4, 5, 6, 7, and the sign is just going negative, positive, negative, positive, negative, positive. Actually starts out as positive though, because if you put in 1, you get 1 plus 1 is 2, -1 squared is +1, so the first term is positive, all right? Now, did I write that on the paper? I didn't write out the series actually. I don't think we have to this time. We kind of get it. So let me tell you this. You are allowed to remove the oscillator that is simply changing the signs. And by the alternating series test discovered by Leibniz, you are allowed to say the limit as n approaches infinity and only apply that to what we call b sub n. The rest of it that's not the oscillator, which is what? What's the rest of it? Isn't it 1 over n? You see it? So if you apply that limit and you plug in infinity, you end up getting, it's just a simple plug-in. 1 over infinity is 0, as discovered in an earlier chapter. Remember test number 1, the divergence test. If you get 0, it's inconclusive. But if it's alternating and you put the alternator in there, it's just enough subtraction of every other term to settle it down. And if you get 0, it is conclusively convergent this time. So this is a convergent series. The slight difference between having the oscillator and not having the oscillator. And I don't care if that's -1 to the n plus 1. I don't care if it's -1 to the n plus 8, cosine of n pi like we used before, whatever it is, if it's causing the sines to oscillate, it's going to work. By the way, I should mention this right now. We'll also go into this later. You will never see sine of n pi as an oscillator because the sine of 1 pi is 0, the sine of 2 pi is 0, the sine of 3 pi is 0. What kind of series is that, right? 0 plus 0 plus 0? Okay. So sine wouldn't work. Cosine does work. Sine you could do in a different way. If you could hit like the half pies, you could hit the peaks and the valleys, but we'll get to that later. All right. So that's interesting. Just, if you graph these, so if you actually graph like n as an x value instead, all right, when you have not the oscillator, but just 1 over n, it just kind of comes down into an asymptote, right? Kind of like this. But when you put the oscillator in there, it's kind of like above, below, above, below, above, below, and then it kind of settles. It's kind of going into like a little rhythm there, and you end up getting convergence, all right? Now, because I'm curious as a cat, I decided to run this through Excel, so we'll do this before we get to the end of the lesson here. I went into my Excel spreadsheet, and I ran this sum of all the terms from 1 to 19. So the Excel spreadsheet put in 1, 2, 3, 4, 5, up to 19, added all of those numbers together. And just to show you something, the outcome was a very tiny number. It was roughly 0.719. Okay, pretty small. Then I upped it to 1,000. So I added the first 1,000 terms of this series. The signs just kept bouncing back and forth, of course. And I plugged the spreadsheet plugged in 1, 2, 3, 4, 5, 6, up to 1,000. Added them all together. And when I did that, I got a very interesting outcome. 0.693, roughly. But it was a long decimal. Rational, by the way, not irrational. It was rational because this is a fraction, right? Fractions are always rational. Imagine getting the common denominator between 1, 2, 3, 4, 5, 6, up to 1,000. But, Excel can do it. Then I ran it to 100,000. Very fascinating results. I got 0.693 also. So wait a minute. By 1,000 I was here. By 100,000 I was there. That's a pretty good indication it was convergent, but you can't always assume, right? But look at that. Not any difference for the first 3 decimal places right there. So now if you go to infinity, okay, Excel can't do that. But this was already proven. All right, this is an unranked mathematician, probably one of the most famous unranked mathematicians. There was a mathematician that proved that when you go all the way to infinity, yes, it is convergent. We just proved it. But what does it converge to? 0.693 apparently? Well, what it converges to is an irrational number. The natural log of 2 is exactly what it becomes. And the natural log of 2 on any basic calculator is about 0.693. So it was rational because it was finite. And then when you go to infinity, it eventually converges to an irrational number with no pattern? Wow, that is amazing. Pietro Mingoli. If that's not Italian, I don't know what is. Pietro Mingoli, unranked, but he proved that this series will converge and that its sum is exactly natural log of 2. He proved that in 1672, which is pretty early on for series. I mean, natural log has just been discovered in the 1600s. In 1672, he published his result in a book. And guess what? In the same book, he actually proved that 1 over n without the oscillator is divergent. He became the first human being to prove this beyond a shadow of a doubt. Even though other mathematicians surmised it was divergent, he proved it was divergent. Amazing in 1672. Pretty good for somebody who's not in the top 100, but I'm sure he's in the top 200 somewhere. So on the last page, we have just 2 quick ones to make sure you understand, and then a little gem at the end. Notice that there's an oscillator right here. That's going to do nothing but just alternate the sign back and forth. Remove the oscillator and focus on the square root of n over n plus 4. Okay, so this is an alternating series, so we will use the alternating series test. We'll do the limit as n approaches infinity of the non-oscillating part. Okay, now cool little thing to notice here, all right? In college note, they actually make you prove that this is non-increasing. Remember that was part of the alternating series test? Okay, in high school, they're all going to be non-increasing because what would be the point? So Non-increasing. Okay, you actually have to, in college, go back to my first semester, do the first derivative test. It starts at 0, so you would block it at 0. Everything just matters after that. If you do the first derivative test on this thing with the quotient rule and set it equal to 0, case 1, case 2, you end up getting 4 as a critical number. You end up finding out that this graph actually is increasing. The little terms are getting bigger at first, but then after 4, they are decreasing to infinity. So what matters? Does this ruin everything? Does this ruin the alternating series test? No. What you learn in college is that all that matters is that eventually the terms start decreasing, or at least stay the same, which would be non-increasing. Okay? So non-increasing eventually, even if not at first, is totally fine. You are allowed to use this test, the alternating series test. Okay? So in college, they'll actually make you do a first derivative test, prove that it eventually is decreasing. It is. Also, if you plug numbers into the square root of n over n plus 4, only numbers like 0, 1, 2, 3, 4, 5, etc., it is always greater than or equal to 0. Okay? The non-oscillating part is always positive or 0, but it's never even 0. Oh, except for at first. When you plug in 0, it's 0. So, passes the test. All right? College, they'll make you prove that. High school, that's a bit excessive. Just wanted to show you how neat that is, that it does eventually go to negative. So what do? All you have to do is do the limit as n approaches infinity of this, plug in infinity, infinity over infinity, indeterminate. And we can't graph it either. Step 2, L'Hopital's, ooh, that'd be a little cumbersome. I would choose the weaker, stronger game instead. So we've got n to the 1/2 over n to the first plus 4. According to the weaker, stronger game, n to the 1/2 is weaker than n to the first. The top one is weaker, and the weaker one turns into 0. And 0 divided by anything is 0. So if the limit, the infinite limit, comes out to be 0, test number 1, divergence test today, inconclusive. Alternating sign, it is suddenly convergent and conclusive. So this is a convergent series. And I leave you off with a nice gem today. So first of all, let's just kind of glance at the sine graph that we all know very well. The sine of pi is 0. The sine of pi over 2 is 1 because it's a peak. All right. Pi is roughly 3.14, right? If you do pi over 2 and cut that in half, it's about 1.57 is about half of 3.14, okay? It's actually exactly half if you were to chop it off there. Now, here's the thing. What if you see the sine of 1? Okay, let's talk about the difference between every class before calculus and AP calculus. Every class before this, even in pre-calculus. The sine of 1 means the sine of 1 degree out of 90, right? The sine of 22 means 22 degrees out of 90, a little acute angle. Everything is in degrees mode all the way up to pre-calculus, okay? Starting in calculus, everything is assumed to be in radians. That is not 1 degree out of 90. That is 1 on a scale of pi is about 3.14. Pi over 2 is about 1.57. 1 in radians is a little bit less than 1.57. So like right about in here, okay? So the sine of 1 is some y-coordinate that is not quite a peak, not quite 1. Who knows what the sine of 1 is, all right? Matter of fact, you can stick it in a calculator. I haven't memorized it because nobody really cares what it actually is. I put it in, I actually got 0.841, or almost peak, but not quite peak. 84% of a peak. Okay, so judging by that observation, the sine of n is not an oscillator. If you see them sneak that into one of your series, that is not a sine oscillator. Because what do you plug in these series? Integers, 1, 2, 3, 4, 5. The sine of 1 is 0.841. That is hardly going to make positive, negative, positive, negative, positive, negative 1, right? Cosine of n, same problem. The cosine of 1 radian is some decimal. It's not positive 1, negative 1, positive 1, negative 1. I've seen this in some of the Vanderbilt classes, sine of 1 over n, cosine of 1 over n slipped in there. Those are not oscillators. They have to be dealt with, actually, on a limit basis. Sine of pi n we mentioned earlier. If you plug in 1 and you get the sine of pi, you get 0. That's not something that produces 1, -1, 1, -1 when you plug in integers. And then finally, cosine of pi n over 2. If you plug in, let's say 1 for n, the cosine of pi over 2 is an x-intercept, which is 0. Every half pi on the cosine graph is 0, 0, 0, 0. Okay? So beware of those. Now, earlier we saw cosine of n pi, or pi n. That's okay. That's an oscillator. Also, by the way, sine of pi n over 2, if you switch these two right here, those do produce 1, -1, 1, -1, okay? But don't ever fall for these as oscillators because they try to trick you. Don't fall for it. See you next time.
Hold it now.
Back in chapter 11, chapter 10. No, maybe it was 9. When is the alternating series? Anybody's thinking like harmonic? Are you kidding me? It's really not part of the particle, so you can't quite the alternating to happen. So you can write this down. All right, if I can spell it. Atler